Good morning, everybody. I am Dr. Hamada Al-Shahar from the University of Strathclyde. Today, we would like to introduce our use case mobility and traffic load management in LiFi Wi-Fi integrated network, which has been made as a contribution to the Deliverable 2.3 primary system architecture. The objectives of this use case: first, to support vertical handover between LiFi and Wi-Fi wireless technologies with handover times less than a specific time threshold. Second, design and validation of a multi-technology coexistent framework for private LiFi and Wi-Fi networks. Third, build a mobility management plane based on the principle of software-defined networking for the LiFi Wi-Fi integrated network. In order to meet these objectives, we have developed this software-defined networking-enabled LiFi Wi-Fi integrated network test bed. This integrated network consists of three planes. We have the application plane, we have the control plane, and then we have the data plane. As you can see, we have also software agents have been developed here in these cells in order to extract the information relating to these wireless channels. The information calculated and extracted by these agents incorporated with open flow information to this as an application in order to provide the intended services in this data plane. This application consists of three parts: real-time monitoring for this network, support user mobility association and disassociation with these access points based on the SNR, and traffic load at each cell in this integrated network. And also load balancing between these cells based on the numbers you associated or based on the traffic load of each cell as well. And here we have the traffic coming in and out from the university network to the network and provide also internet connectivity. This test bed has allowed us to realize the experimental handover management scenario where we can see when a user moves from a LiFi access point 1 to LiFi access point 2, and then from LiFi access point 2 to Wi-Fi access point. Over 1 minute during his path from access point 1 to access point 2 LiFi, and then to Wi-Fi, we observe that there is a shorter delay this user device underperforms moving between this LiFi access point comparing to Wi-Fi, though here it was running in a buffering mode, so it's not experienced any service disruption. But what's important as well as they move in a new cells, so the channels are available and it picked quickly their average video streaming data rate. In order to move to another scenario, so we picked a more denser scenario where we have a user associated to a cell, and then umbrella, and this is umbrella we ported from a graph theory where a spanning tree is established around the serving cell, plus the wider coverage here we have Wi-Fi access point in order to provide him sort of a continuous mobility space using, of course, software-defined networking. This is here, I mean, the admission of users to this, our connection to this tree is based on tree-based admission and cell, which is two layers. So first, here the application assess the number of channels available in all the cells in the tree, and accordingly can manage or deny admission for a connection in this network. This is analyzed using a queuing model. So we have the arrival to a cell is lambda. We have the exponential services. We have Poisson here. We have also M, and then we have number of channels in each cell, and then we have number of requests are coming. And according or based on the different relationship between handover dropping probabilities and forced termination probabilities and load per cell, which you can refer to deliverable, we can define these handover dropping as if a user moves from a cell to adjacent cell that can be dropped because of lack of channel resources. Forced termination probability is that during the lifetime connection, the connection is admitted, but it's terminated because of handover dropping probability or because also lack of resources. Based on these models, we would like to show you, the obtained results. As you can see, the handover dropping probability and the forced termination probability, the handover and the forced termination probability, both of them increase as the load per cell also increase, because all it's related to available channels in each cell. But what's important as well is that the probability, the tree-based admission probability, once it's running, increases. The increase of this probability, that means also decreasing the handover dropping probability. So ensuring a sort of admission control at the level of a tree could decrease the handover dropping probability and the forced termination probability. So in order to guarantee a specific equality of service metric, whether in terms of handover dropping probability or forced termination probability, you need this value to be adjusted to certain threshold, or to run the admission control at the level of the tree. So in a heavy environment, in a heavy traffic environment, it's really difficult to meet sort of a low handover dropping probability or forced termination probability with low admission control at the level of a tree. So both the two layers, admission at the tree and the cell, is important in order to guarantee the quality of service for admitted connection. As a conclusion here, the software agents have a great role in enabling seamless heterogeneous wireless networks integration. The tree-based admission control can effectively reduce the handover dropping probability in comparison with the tree-based admission control. This is the same also for the for the forced termination probability. And in order to guarantee them a certain, it has to be large, the admission control, in order to meet the quality of service guarantees for admitted connection. Thank you very much for your attention, and hopefully to see you soon. Thank you.